All right, so today's class we're taking a look at implicit differentiation. So what that means is that sometimes there are situations where we can't solve an equation for y, or it's very difficult to do so. So let's take a look at a problem that's very basic where we can solve for y, but we're going to go ahead and differentiate it. But let's take a look at that first. So if we have negative 2x plus y equals to 4. Okay, so in this case, I could just go ahead and see that this is a linear equation with a slope of 2 and a y-intercept of 4. Pretty straightforward. So my derivative is just going to be negative 2. But let's say that we can't actually solve for it. And we'll look at one in a minute where you can't. But here, if I take the derivative of the individual terms, which we've seen we can do previously, okay, so the derivative with respect to x in each of those. The first one right here is just going to come out to be negative 2, as we've seen previously. Now, the next one, dx, so the derivative of y with respect to x, we know that that's just going to come out to be dy dx, as we've seen before. Okay? And then the derivative of a constant is just 0. Okay? So in this case, I was trying to solve for the derivative of y with respect to x, which means that I'm just going to isolate dy dx. So I just end up with 2, which is the same result we would have gotten if we had just gone ahead and solved for y in the beginning and then taken the derivative. Okay? So pretty straightforward. But if we have a situation that's a little more complicated, like say we have a circle, x squared plus y squared equals to 4. And we're asked to go ahead and find the derivative of this. Well, we could definitely solve for y and then have the square root, or plus or minus square root of that expression, of 4 minus x squared. But there we'd have to differentiate two different functions here. But if we look at this thing here, and we do the derivative of the individual terms on the left-hand side and do the same thing on the right, I'm going to end up with 2x here. And then just like we did in the last one, I'm going to do the derivative of 2y squared, which is just 2y. But just because we took the derivative of y with respect to x here, so just like in the previous problem over here, we ended up with that dy dx, we're going to end up with that dy dx also over here. Okay? So the reason we're doing that is because it's a reminder that we're taking the derivative of y with respect to x. We don't have to do that on the first one because it's the derivative of x with respect to x, which is dx over dx, which is just 1, right? So it doesn't need to be written in there. But you're doing the derivative of y with respect to x, so that's why we have that dy dx. A quick way to remember is if you're taking the derivative of a variable that is different from what you're doing the derivative in respect to, so the denominator is that dx right there, you're going to end up with a dy dx. If it's an r, it'd be dr dx. Okay, but in this case, we're trying to solve for the derivative, so all I have to do to actually find it is to solve for dx, or sorry, dy dx. Okay, so 2y dy dx equals to negative 2x, and I'm just going to divide both sides by 2y. And I can simplify those 2's right there, so dy dx is just going to be equal to negative x over y. And so that's the derivative of that function up top, which means that it's the slope of the line that's tangent to that circle at and then a given point, whatever you want to plug in there. Okay? So these definitely get more complicated, but that's the basic idea that we're looking at for these. Okay? So check the solutions and see if any of this helps out. And we'll definitely spend some more time on this over the next class too.